Good morning, good afternoon, or good evening. It's my pleasure to be with you today. I'm going to give you a short presentation on how I have recently been involved in applying geochemical mapping to forensic and intelligence. This work is the result of a collaboration of many of my co-workers from the Australian Federal Police, Geoscience Australia, the University of Canberra, Flinders University, and the Australian National University. Motivation for this work is that Geoscience Australia started a collaboration in soil forensics around 2016 with the University of Canberra and the Australian Federal Police. At the University of Canberra, there is a National Centre for Forensic Studies that is a joint venture between the University of Canberra, the AFP, and the Canberra Institute of Technology. In 2017 and 18, I was able to take up a secondment opportunity to spend a year embedded with the forensics chemical criminalistics team at the Australian Federal Police in Canberra. And the aim of this secondment was to further develop their soil provenancing capability. So the key question that I will address in this presentation today is, can the composition of a soil sample from a crime scene be used to indicate its provenance or origin? Today's presentation will consist of a short introduction, followed by a detailed look at the sequential and simultaneous empirically based soil provenancing approaches. We will then have some conclusions. Soil is a mixture of minerals, rock fragments, sometimes man-made particles, often organics, and very commonly water, air, and other volatiles. There are many ways that we can characterize soils, either looking at the bulk properties, the chemical elements, isotopes, minerals, the organics themselves, or the gases. In a word, a soil is a highly complex material. So all these properties vary laterally, and that's why we are able to create maps such as shown at the bottom of this slide. But they also vary vertically, which is the formation of horizons in soils during pedogenesis. So the scale of heterogeneity is very important in this context. And it can essentially vary from centimeters or even millimeters or microns if we look at crystal boundaries to hundreds of kilometers. And traditional geochemical maps have been used in resource and environment application. In applying soils to do some forensic provenancing, Barry Rawlins and co-workers in 2006 wrote that predicting the provenance of a sample of Earth-related material is one of the most difficult and challenging tasks for analytical Earth scientists. So one approach developed during this secondment to tackle this challenge is as follows. We obtain soil property values, either we get them from databases or from models, or we can actually go out in the field, do a fresh sample collection and analysis. And therefore we have either predictive or empirical provenancing, depending on whether we use existing models and databases or something that we go and collect and do a geochemical survey ourselves. We then create maps of the distribution of these properties across the study area. And conceptually, we find the equivalent contours of the values representing the question sample or the evidentiary sample, which is a target value plus or minus an uncertainty, and we call that the search range. We can do this in a geographical information system. Once we've done that for one element, we can do the same for other soil properties or other analytical methods, and also or statistical summaries of those data, for example, principal component analysis. So we can essentially prepare a series of maps that show where in the study area the soil within uncertainty corresponds to the evidentiary sample that we want to provenance. Let's now look in detail at the sequential approach. So the sequential approach essentially does exactly what I said in a couple of slides before, where we actually prepare maps that match the evidentiary sample, one element after the other. And we essentially give a score of 1 for every pixel where that match is within the uncertainty, and a score of 0 where it isn't. And we can then do this for example, 38 elements from ICP-MS analysis and add up all these scores for each pixels. So the demonstration of this approach was done in the North Canberra Urban Soil Geochemistry Project, which is a collaboration between the AFP, UC, and GA. We collected 268 sites in natural reserves, parks, and pasture land that surrounds Canberra at an average density of 1 sample per square kilometre. We collected the top 5 centimeters of depth below the plants and the root zone. We air dried and sieved to 75 micron, and we collected some quality control samples as well. In addition to these survey samples, 3 blind samples were taken by forensic scientists, unbeknownst to me. Their location was not known to me, and these were analyzed with the others, and the aim was to use these 3 blind samples to see if I could, or if this method could correctly predict their origin. Here you can see the study area in the northern part of Canberra, in the Australian Capital Territory in southeastern Australia. There's a Landsat image, a cadastral image showing the built-up and recreation and reserve areas, the soil types, the lithology, and the stratigraphy. For the geochemical survey, the methods used were, we used an interpolation using inverse distance weighting with the power of 3, which we found was the most reliable interpolation method. The cell size was 250 by 250 meters, and we wanted to map the possible location of the questioned or evidentiary samples based on their target value plus or minus the uncertainty. And the uncertainty included both the measurement uncertainty and the interpolation uncertainty. The analytical methods used for the provenance analysis were the Fourier transform infrared spectroscopic method, magnetic susceptibility, X-ray fluorescence, including loss on ignition, total digestion ICP-MS for minor and trace elements, and aquaregia digestion ICP-MS, giving us a total of 97 variables, including 27 principal components. We analyzed these data either sequentially, simultaneously, or using a Bayesian approach. I will discuss the first 2 today. The third one is under development and cannot be fitted today. So this slide shows the results of the sequential multivariate analysis for ICP-MS using 38 parameters or 38 elements that were determined in these 260 odd samples and interpolated. And the maps that you see in the left panel, so A, is for the location or the prediction of the location of the sample blind 1, in B for blind 2, and in C for blind 3. And essentially, the warmer the color, the redder it is, indicates that more of the 38 elements or variables determined by this technique match the blind sample at that particular point. So if you look in the lower panels of these maps, you can see the detail of blind 1, blind 2, and blind 3. And you can see, for example, that blind 1 has a relatively poor predictability. So only about 13, in fact, of the 38 elements matched what the geochemical map would have predicted. In blind 2, we have 31 of the 38 variables that match, and for blind 3, we are at a value of 17 out of the 38 variables that match. The reason for the relatively poor match of blind 1, we believe, is that this sample was collected in an atypical environment for this particular square kilometer of land, so it would not have been very similar to the sample collected for the geochemical survey. And that was done on purpose by the forensic scientists who collected that sample to sort of test how far this technique could be pushed. And obviously, this comes back to the question of soil heterogeneity. Soils can vary greatly within a meter or 10 meters. For example, there's a swampy area within the square kilometer that we're trying to represent with the geochemical survey sample, but clearly the composition is going to be different for that unusual environment. And that is what we are seeing here with blind 1. So we won't have time to go into more maps of this approach today, but we'll give you the reference of the paper in the next slide. But basically, this approach, using the sequential multivariate approach, we can conclude that the 3 blind samples showed a range of provenancing performance, and that is reflecting the inherent challenge of natural soil heterogeneity. So it is still a very challenging thing to do. The empirical provenancing we found and we recommend should prioritize Fourier transform infrared spectroscopy, magnetic susceptibility, and X-ray fluorescence analysis as the most effective methods. And that is followed by ICP-MS for either the total or the aquaregia digest. We found that combining mineralogical information, for example, from FTIR or MAGSAS, and possibly also adding X-ray diffraction in the future will greatly enhance the performance of the provenance analysis. And having access to as comprehensive an analytical suite as possible is an advantage in forensic provenancing. And we also found that the inclusion of the principal components in the provenancing workflow provides a marginal advantage in terms of provenancing performance. So here's the reference to the paper that covers this approach in greater detail. It comes from the Journal of Forensic Sciences in 2021. Let's now look at the simultaneous approach. The simultaneous method is essentially based on the calculation of a correlation coefficient between all the variables of the blind sample with all the variables in all the other samples. So essentially what we do is we calculate a Spearman correlation coefficient, which is essentially a correlation of the ranks. So the first thing we do is we rank all the samples, all the analyses from 1 to 330 or so, which is the number of variables that we have. And we calculate the Spearman correlation coefficient of each of the 3 blind samples with all the other sites, all the other geochemical survey samples. And we find either a negative correlation coefficient, a neutral one, or a positive one. So this is, for example, shown on the diagram on the right with the blue, orange, and the gray dots, respectively. And then we can prepare a map of this Spearman correlation coefficient, and we can essentially do the same kind of analysis using interpolation, and then we can match the areas or predict the areas where the match is the greatest for all the variables at once. At the bottom right here, you can see that for the number of samples that we have, which is 268, a Spearman correlation coefficient of greater than 0.1 has a p-value of 99.5. So here is a map showing the results of this simultaneous multivariate approach for the Fourier transform infrared spectroscopic data. So in this case, we are looking at approximately 5,000 variables, which are all the wave numbers that are produced, that are at which adsorbance of the infrared electromagnetic radiation are measured. So it's got a really high number of variables. And the Spearman correlation coefficient obviously varies from -1 to +1, and these have been colored from black to red, with the neutral being white around 0. And so we can see the map of prediction for blind 1, 2, and 3 in the upper panels here, A, B, and C, respectively, with the greater details shown at the bottom. So for blind 1 on the left, we can see that we have a prediction correlation coefficient of -0.16. So it is sort of neutral, but slightly negative. For blind 2, we have a Spearman correlation coefficient of 0.5, and for blind 3 on the right of 0.4. So again, we see a range of performance, with blind 1 having the same problem as before because of this sampling location issue that I have mentioned. So the conclusions from the simultaneous approach are that the 3 blind samples also show a range of performance in the provenancing results. The best methods were FTIR and XRF, followed by total ICP-MS, and then finally the less good one was the aquaregia ICP-MS. Again, we found that combining mineralogical information from FTIR here, but potentially also XRD in the future, can greatly enhance the performance of the provenancing analysis. And again, having access to as comprehensive an analytical suite as possible is advantageous in this simultaneous multivariate approach. And we can exclude up to 75% of an area. So the overall conclusions for empirical soil provenancing that was shown using two methods that we developed, the sequential one and the simultaneous one, through a pilot project in the Australian Capital Territory, show that FTIR, magnetic susceptibility, X-ray fluorescence, and total digestion ICP-MS were the best methods that were used, with the ones in bold here being most precise and accurate for the provenancing analysis. And these metrics are explained in the papers that I have and will mention. We had a total of 97 variables, including principal components, and we did spatial analysis using an open access GIS. The sequential, simultaneous, and probabilistic multivariate approaches were proposed. And despite being a highly complex task, the potential has been demonstrated, we think, to use soil as an evidence class for forensic provenancing, at least in an intelligent context, and particularly in combination with other evidence. So due to time limitations today, I won't be able to go into the theoretically based provenancing, but I'll just be able to show you the paper in which we have presented this work. So this is the paper on predictive soil provenancing, which was also published in Journal of Forensic Sciences, in this one in 2019. So it is now time to draw some overall conclusions of this work. So the overall conclusions of this work are that empirical soil provenancing using soil geochemical and mineralogical surveys has the potential to be useful for forensic provenancing. Sometimes suitable surveys or databases may not be available. Soil heterogeneity at various scales poses still a challenge. There are a number of properties that can be included in this approach, and if we start looking at things like soil microbiome DNA, then we virtually have a limitless number of variables that we can include. Predictive soil provenancing is a promising novel forensic and intelligence tool. It's based on soil property rasters at high resolution, 90 meters or less, and they are becoming available more and more around the world. So this work on soil provenancing using geochemistry needs further validation and refinement, but we believe it is sounding promising. And with this, I thank you for your attention.